Thanks, and good evening, everybody. Thanks for coming. My name is Russinovich. I'm the Chief Technology Officer of Azure. Let me actually get one of these other mics. And tonight, what I'd like to do is share a little bit about Azure Momentum and talk a little bit about Azure's scope globally and how the Azure government fits into the big picture. And then I want to drill into Azure and security and talk a little bit about some of the ways that we want to push cybersecurity forward. Those of you that were in the talk I gave at Cyberscoop this morning, how many people were there, just out of curiosity? Okay, so you're going to see some repeat here, but I'm going to go a little bit deeper and I'm going to show some demos of some of the stuff that I talked about this morning. So I'll start by talking a little bit about Azure's Momentum. And if you're not watching the news, if you're not listening to our earnings reports, you might not be aware of just how big Azure's gotten at this point. I've got some what we call shock and awe statistics up here to kind of convey the scale that we've gotten to and also show some other interesting metrics that are relevant to a lot of customers. You can see some huge numbers over here. For example, up in the top right, that's Event Hubs, which is our event ingestion system. It's similar to Kafka, and it's used for IoT as well as for inter-service communication in the cloud. And we've passed 6.4 trillion messages per week. We've actually exceeded 1 trillion messages processed on a single day. And that's a pretty staggering number by itself. But I think what really makes that number cool for me is that I've been talking about Event Hub's throughput for about a year and a half since it went GA. So I've seen this number continue to go up. And just a year ago, that number was 5 trillion per month. So this is the kind of representative of the growth that our services are experiencing and the scale that they've gotten to. You can see another one down here, Azure Database. This is our database as a service offering, SQL, MySQL, and Postgres. And we've got now close to 2 million databases active at any point in time, processing over 1 trillion database requests per day. Azure Storage, 130 trillion storage objects. And then I've got some statistics here, like I said, that it might be interesting to you. How many people use open source? So that's great. You might be surprised to hear a Microsoft person saying that's great, and I'm saying it honestly that it's great. And I used to actually be in Windows, but I think it's great. And this number up here, this Linux number, we just passed 40% of our virtual machines that we have operating in Azure are now Linux virtual machines. This is a long, great path that we've taken towards open source. In fact, Azure was the first major Microsoft property that really embraced open source. When we went out with infrastructure as a service, we went out day one with both Linux and Windows. And we recognize that our success in the world today requires us meeting customers where they're at, and many customers choose Linux. Linux is actually a fantastic operating system for cloud native development, and so we have to be great at Linux. This number, I don't think we're happy necessarily with where this number's at, because if you take a look at cloud native development, there's a bigger percentage of it happening on Linux and Windows. That said, how many people use Windows? Okay, we love that too. We still love that and continue to use Windows, and we want to make Windows great for you so you can continue to use it. The other number up here that's interesting, I think, is Microsoft's largely recognized as being great at the enterprise. But we believe that we can't be a great cloud just focusing on the enterprise. We've got to focus on ISVs, and we've got to focus on startups, the next generation of ISVs. And so this number right here, 40% of our revenue actually does come from those two communities, 60% from enterprise. So we feel pretty good about this number, about getting traction with the ISVs and startup community. Now, those were some numbers that represent our scale. Here's another view of our scale. This is our Microsoft global infrastructure, and I say Microsoft, not Azure, because Azure is now the foundation for Microsoft. Every Azure data center is a data center for all Microsoft services. Xbox Live, Dynamics 365, Office 365. All of Microsoft services are built on top of the Azure platform. And so our global infrastructure now spans 42 regions around the world. We've announced 42. In fact, today we kind of announced some more, but we haven't really specified that they're new regions. And 38 of them are already operational. So you can see that we span everywhere from the first cloud being in South Africa, Australia, a bunch in Western Europe. More and more we focus on countries as a geography. And this is a unique aspect of the way that we handle customer data, which is we believe customers are in control of their data. They get to say where they store their data. We're not we can't move their data without their consent out of a data center, or rather out of a region. And so we define what are called geographies, where customers know that their data will always remain inside that geography. That geography is aligned, hopefully, with the customer's comfort on having their data be anywhere in that geography. When we started Azure, geographies meant things like Western Europe. But more and more, the world is changing to be more focused on sovereignty, and data stay within country boundaries. And so that's the direction we've gone. And we've got French regions. We've got English regions in the UK. We even go a step further, where some countries have more stringent requirements around how their data is handled, government data, for example, or financial data within that country. Germany is a great example of that, where they're not comfortable having non-German citizens handle data because they're very concerned about data privacy of their citizens. So we have what we call a sovereign cloud in Germany, where we don't operate it. A German entity does, T-Systems, which is a subsidiary of Deutsche Telekom. And that means our DevOps engineers can't simply go push deployments into that region or access that region to do DevOps troubleshooting. They have to request access. They've got to request permission to deploy, and then they get escorted in. We've got that same operating model in the US government cloud. We've got 6 government cloud regions. 2 of them are specifically focused on the DoD, and these have the highest levels of certification of any of our regions. And they're also not operated by us. They're operated by a third-party contractor that the US government, of course, approves of. And like the German data centers, we can't access them directly. The other cloud that we've got that's like that is our China cloud. So we've got 2 regions in China. And you'll notice I'm saying even numbers when I talk about regions inside of a geo, and that's very deliberate. This is another unique aspect of our strategy when it comes to data center architecture, is that when we go into a geo, we go in with 2 regions specifically so that customers can build a disaster recovery solution on top of us without having to worry about taking their data out of that geo. So for example, in Germany there's 2 regions, in France there's 2 regions, and that allows people to make their base in one, and if something happens to that region, large-scale natural disaster, large-scale electrical grid failure, they can fail over to the other one and keep their data within the geography. We also have a huge global network here. You can see the lines here on this, and this represents, we're one of the largest networks, probably up at the top few global networks on the planet. We've got 30,000 miles of cable. We just laid down a new cable, launched a new cable called Maria just a few weeks ago that crosses the Atlantic. It's 4,000 miles long. It's 160 terabits of bandwidth, the largest of any subsea cable. It was a joint project between us, Facebook, and Telxius. And another unique aspect of this cable is that unlike most of the cables that go across the Atlantic that go from England to New York or New Jersey, this one goes from Spain to Virginia. And that was also a deliberate choice because Hurricane Sandy actually put our connection points for our subsea cables and everybody else's that land in New York and New Jersey at risk. We realized big single point of failure for cross-Atlantic communications. And so we, with Facebook recognizing this risk, went in with them on creating this, laying down this cable. And we've got other big cable projects like that underway. Now, a few years ago, how many people actually, let me take a survey, how many people, say 4 or 5 years ago when cloud was starting to hit people's radar, thought, you know what, cloud sounds interesting, but for my line of business, for my workloads, for my data, it's never going to be secure enough? So a few people. And I think some of you are probably lying at this point. And the fact is that most people, and I'm not saying all people, but most people now feel that the cloud is actually very secure. In many cases, it's actually more secure. They admit it's more secure than the security that they've got for their infrastructure on premises. I think more and more people are starting to recognize that the cloud offers an opportunity for more secure applications as well, not just the infrastructure. And let me explain why. First of all, Azure has very secure data centers and infrastructure. Everything from the best world-class data center physical security, so gates and biometrics and metal detectors and requirement for access to a specific colo, again with biometrics and cameras everywhere and security guards. no data ever leaves the data center. It's all destroyed on its way out if there's devices storing data. First-class physical security. First-class operational security as well. So this device that, just an example of this device that I'm presenting on is my everyday laptop. This is what we call a secure admin laptop, and let me show you what that looks like. Actually. So here's the lock screen for this thing. You can see it says Secure Admin Workstation. Now when I log into this, I'm using multi-factor authentication using a virtual smart card. Hard to type with the mic in my hand, hold on. And what I'm landing on here is a desktop. This is the desktop that all DevOps engineers use to access production with. It's a fully locked down Windows 10 system with whitelisting, app locker, and device guard in place. So only authorized software is allowed to run here, and only authorized websites are allowed to run, and the only browser, of course, is Edge. So you can see how serious we are about security. Now, what I just opened up here and what I'm doing my presentation on is a virtual machine sitting on that host. This virtual machine is the insecure domain that I do my everyday browsing and view PowerPoint slides on. And so this protects access to production. And production access is also just-in-time access production. It's just-in-time and it's least privilege. So DevOps engineers that need access to a particular resource in production have to reference a ticket that's been opened by somebody else, an incident ticket that specifies what resource they need access to. They granted time-bound access just to that resource. Everything is logged on their way in through JIT, and all the operations they perform are also logged. So this is world-class operational and physical security as the platform that you build things on top of. And now when you build things on top of it, the cloud also offers a fantastic opportunity for you to have insights into the way that your applications and network operate that are extremely difficult or impossible to gain on on-premises networks, especially ones that have grown organically and consist of lots of different types of routers and firewalls and virtual appliances and physical appliances and servers, and you get the idea. Lots of different applications and operating systems and so on. With the cloud, anybody that's worked in here that's worked with the cloud knows that it's got APIs, and those APIs are designed by the cloud provider like us to be extremely uniform across the platform. That means that every resource that we model in the cloud, every PaaS application instance, every virtual machine instance, every network object, all are represented by API-driven objects, which means with the appropriate authority or access, you can go and enumerate all of the resources that you have access to and understand the relationships between them. So you can go look at all your virtual machines. You can look at their network adapters. You can see what firewall rules, SDN firewall rules they've got on them. You can see, using the logs that come out of the system everywhere, that you can plumb into your own accounts and then analyze exactly what those virtual machines are talking to. So everything is there visible to you, either in logging or through APIs, in a very consistent manner. And this is something that allows you to have a very solid idea of what kind of security you've got in place. And then finally, on top of this, we have been focused on doing these kinds of API-driven modeling of our environments ourselves. We also spend a lot of research and energy on fine-tuning machine learning algorithms for cybersecurity. And I've talked about this at the last two RSA conferences, some of the work we do with machine learning and cybersecurity. At the scale that we're at, billions of objects in some cases, we cannot sit and have humans looking at anomalies and say that's a security incident or not. We need machine learning to tell us. And so with all these signals that we've got from Office 365, from Azure, from all of our other services, from our threat intelligence networks, we apply machine learning to tell us when there's an incident. Not only that, but to tell us with a high degree of probability it's a real incident, and connect the dots on where an attacker might have done and moved laterally throughout our systems, even through disparate types of services. We take that same technology and we try to make it available to customers with security as a service. One example of that is Azure Active Directory Identity Protection, where we're using machine learning to profile basically an organization's logon patterns, where they are logging on from, what time they're logging on, what devices they're logging on from, what type of authentication they use, and modeling those so we can identify with a high degree of probability an anomaly. Potential sign of an attacker logging on and using it because they've compromised somebody else's credentials. And then sending an alert to that person or step-up authentication, requiring step-up authentication for that person to gain access to their services. Now, all of this has allowed us to achieve the industry lead in terms of certifications. That's another thing that we focus on, is taking all the security controls we've got and basically having a catalog of them. And the way that we achieve certifications is to take the controls from the certification, map them on the controls we have. We have evidence for each of these controls that we can produce at will, and then we go and get the certification. We've got 70 certifications now, and you can see that they're in international standards, they're US government certifications, they're industry verticals, and they're even regional. So UK, England, Japan, specific certifications for those different geographies. We are in a constant state of ready to certify. You have to be when you're at 70 certifications, which means that we have constant evidence collection. At any point in time, somebody can come and say, hey, renew your FedRAMP High, and we can produce a body of evidence that represents our adherence to FedRAMP High controls. And that is, again, based on top of the fact that we've got very secure operations and infrastructure. As far as security services, I mentioned Azure Active Directory Identity Protection. Here's another one, and this is one of the announcements we made that Karina talked about for US GovCloud, is Azure Security Center. So those of you that have worked in security know that getting a new security product, validating it, figuring out how to use it, deploying it across your infrastructure, keeping it up to date, listening to its telemetry, its reports, and its incidents, is non-trivial activity. And many a career has been broken on trying to keep their cybersecurity systems up to date, especially when they're all different and competing with one another or filling in one part of the puzzle. What we can do, again, on this API-driven world, with the machine learning on all the telemetry that we collect, is provide security as a service that will tell you when your virtual machines are unpatched and what vulnerabilities they're exposed to, what IP addresses they're talking to that we know through our threat intelligence networks are owned by somebody that have been blacklisted. We can tell you by looking at the topology of your architecture that you've got an HTTP port that's sitting exposed to the internet that should be behind a web application firewall. And again, through APIs, right from this portal, you can deploy a web application firewall from our marketplace and put it in front of that. This is all through the power of APIs in the cloud. Now, with all of this security, that meme from a few years ago of the cloud is just not ever going to be secure enough for average everyday IT workloads, much less very sensitive data, has eroded. And we see lots of companies looking at us and saying, like I said, you're doing it better than we do it. A great representation of the progress we made in this space is with financial sector. Financial sector, of course, very sensitive data. If it's lost, it's compromised, it puts their business at risk, it puts lots of customers at risk. In the case of some of the banks and the financial institutions, about 25, they're called GSIFIs, Global Systemically Important Financial Institutions. If something happens to them, the global economy is impacted. You can see from the stats over here that 85% of those GSIFIs have signed cloud terms with us to start moving workloads. And some of them have started to move significant workloads. Other ones have just begun to look at how to move workloads. But you can see a sample of the banking customers going big, meaning they're moving big stuff onto us. They're in progress or started the projects to move big workloads, including core financial workloads, onto Azure. Now, here's another big company that we're very proud to have on the platform. Again, I think they were very concerned about security. Actually, I don't think they care about security at all, but how many people watch the HBO show Silicon Valley? Okay, so it's my kind of audience here. It's for those of you that don't watch it, you have to watch it. It is a very accurate parody of what goes on in the real Silicon Valley. But the fictitious company that's in the show is called Pied Piper. And this was heartening to me this season because they're in this was season 3. In the first 2 seasons, every now and then they talk about using the cloud, and of course they would talk about using another cloud, not Azure. Well, this season they actually talked about Azure. Not only that, they signed up and are using Azure. This is a screenshot from the TV show of the Azure portal. So that was, we've broken, you know, for Microsoft to actually be talked about by somebody in the Valley, not just somebody in the Valley, but a parody show about the Valley, shows that Microsoft's come a long way as being a cool company, a hip company that it wasn't 5 years ago. 5 years ago, nobody in the Valley was even concerned about Microsoft. You'd say Microsoft, they'd say who? Because they're all walking around with Apple laptops and using Linux. Now they're using Linux on Azure. So with all of this security that we got in place, we're never satisfied. And I'm passionate about cybersecurity. So I've been trying to push the envelope with us in cybersecurity. So some of the basic capabilities that are required for cybersecurity in the cloud include, of course, encryption at rest. This is one of the first kind of security features that financial institutions and other companies came to us with. Encryption at rest, because that was really kind of a regulatory control from on-premises world where your physical data center security wasn't necessarily the best, and it was possible for a disk drive to walk out of the data center. And at that point, you've lost your data. It's leaked. The cloud physical security controls are such that the risk of that is almost negligible. Nevertheless, it's great to have this extra layer of defense, and also we require just to unlock or unblock some companies that have this as a regulatory requirement. So we've got encryption at rest in 2 forms, server managed keys as well as customer managed keys, where customers can bring their keys, store them in our HSM, Azure Key Vault, and then encrypt for, sounds like something not good happening out there. Oh, is it? Okay. Something, okay, never mind. So you get this extra layer of defense, and you can control the use of those keys so that if you revoke them, of course, the data is no longer accessible in the cloud. We also have encryption in transit. So whenever we're transmitting customer data, for example, from one region to another because you've opted into geo-replication of data for disaster recovery, we are encrypting everything that goes across the wire. What's been missing up to now has been encryption in use. Now, let me explain what encryption in use is. A lot of customers say, hey, the cloud is not quite ready for data X or workload X. And why? What kinds of workloads are there? Financials, very sensitive financial data. There's still some banks out there and financial institutions that will say this financial data is just too precious and high risk to put in a cloud environment. Or the plans for my next generation product, and it could be a weapons platform or something else, just too sensitive to put up in a cloud environment. Or this health information, too sensitive because if it leaks, I'm in a regulatory problem, I'm compromising the trust of my customers. Or just customer PII, I don't want to have exposed. And we've seen some high-profile breaches of PII recently that really demonstrate that particular problem. And some of the people believe if I put it in the cloud, I'm at more risk of something like that happening. The cloud is all about not just storing huge amounts of data, but processing huge amounts of data. Every company is becoming a data company, and many of your organizations are already, you know that your whole business is around data. What you want to do, though, is get insights and intelligence out of that data, and that requires processing it. So you're actually not doing much good if you're storing a whole bunch of data in the cloud, but you can only process it on-prem, unless you view the cloud as just it's my backup site. But ideally, we believe you'd want to and can take advantage of the capabilities of big data analytics platforms, our scale-out PaaS services like Azure Database that I talked about, our NoSQL database Cosmos DB, if you can overcome that sensitivity. What if I could put my data in the cloud, have it be encrypted at rest, have it be encrypted in transit, but I could also have it processed, effectively encrypted. And by that I mean nobody has access to it. Just like they don't have access to the encrypted data on disk because I've got the key, they don't have access to the encrypted data while it's being computed over because I've got the key. That, we think, could fundamentally change the game and unblock a lot of business, the kind of long pole, the tail of people with security concerns in the cloud. It's also important for us, though, from another perspective. If you think about cybersecurity, it's about staying one step ahead of the attacker. It's about raising the bar. And we believe that encryption of data in use is actually another way to raise the bar on data protection. If you can minimize the surface area that that data is exposed to, you can be confident that it's more secure. So this kind of technology that I'm about to talk about, we believe is a fundamental game changer for cybersecurity, for not just getting customers that are reticent about moving things into the cloud, but just about raising the bar on cybersecurity in general. And this is applicable to the cloud. It's also applicable to IoT as well. And you'll see as I explain this. That technology we call Azure Confidential Computing, or ACC. And we announced it this summer as a preview, or we announced it in September. So it's been a little over a month since we announced this, the preview to this. We've been working on this for 4 years. It's a combination of Azure and Microsoft research on this with Intel and with the Windows team. Now, trusted execution environments is the foundation for confidential computing. They're called TEEs. And we've built a TEE in software in Windows 10, Windows Server 2016, called Virtual Secure Mode, or VSM. Virtual Secure Mode effectively is the hypervisor creating a Hyper-V partition, a virtual machine, that only runs a small piece of code, where that small piece of code has to meet certain criteria to even be allowed into the enclave, it's called, or TEE, and where we've got an attestation service where the hypervisor's got a special key and it can sign a quote that it can be used to attest to somebody outside that that piece of code is a specific piece of code meeting a certain signature and that it's being protected by a VSM enclave. Like I said, we've also been working with Intel. Intel's got a technology called Software Guard Extensions, or SGX, that's in their Skylake processors. It's similar to VSM in that these SGX processors have a key that's been provisioned by Intel. And you can create a SGX enclave and then load code into that enclave. When that code is loaded in the enclave, you can ask SGX, the processor, to provide a quote of what code is running in the enclave. And it will give you back a signed quote of a hash of the code that's running in the enclave. And you can look at it and say, yep, SGX is protecting an enclave that has got this piece of code that I stored in it. Now that you know exactly what code is in the enclave, and you trust the enclave to protect that code, and you trust the code itself, now you can allow that code to access data, very sensitive data, knowing that the enclave is protecting it. In the case of Virtual Secure Mode, not even an administrator on the Windows Server box can get access to the contents of the enclave. There's no APIs, programmatic way for them to do so. Attacker, a malicious insider that tries to get in. A hacker that breaches some part of the multi-tenancy boundary and gets the foothold on the server can't get in the enclave. The hypervisor is protecting it. And then, this is important for a lot of our commercial customers, and it might be important to you too, is I don't want a third party to access my data without my consent, without my knowledge. Now, that's one of the concerns they might have in a public cloud environment, is if I put my data in the public cloud and then some third party comes and coerces through legal means the cloud provider to release my data, maybe I can get it. Now, this is one of those things, like encryption can be used for good and evil, and so I want to just get ahead of that. But fundamentally, this is good for security. Now, let me talk about some of the scenarios we've been exploring with this, and so some of the things that you can do with this kind of technology, because it's not just about creating a black box and sticking some code in it and processing it, but like, what can you fundamentally do with that kind of power and capability that you couldn't do up to now? And the first example I'll talk about is SQL Server. So we've got Azure Database, which is SQL Server as a service in Azure. You can, within a few minutes, or a few seconds actually, go create a SQL Server instance in Azure, and then create tables and load data into it. Now, SQL Server has had this feature for a while called Always Encrypted. Is anybody familiar with Always Encrypted? So a few of you are. And Always Encrypted lets you take a client-side key, encrypt particular columns as you load data into the database, and those columns now are not ever in the clear in the database, on the database server, or in the case of Azure database, in the cloud. And that makes you confident that this sensitive data, these sensitive columns, are never exposed to the cloud provider, malicious insiders, or these other threats. That has some limitations, though. The big one is that you can't do complex queries on that encrypted data because it's encrypted. SQL doesn't know the value of the data, and it can't do range expressions, it can't do aggregates, it can't do maxes and mins on it. It might be able to do some basic equality if you've got a deterministic encryption algorithm, but that's it. So really, you can't really get insights out of that kind of data. Now, with the case of enclaves, with the use of enclaves, SQL is going to introduce a next generation of this capability that they're codenamed Always Encrypted VNext, very clever code name. What this does is uses the power of an enclave, SGX enclave or virtual secure mode enclave, where the SQL query processor is inside the enclave, and you load your encrypted data into the database. You encrypt columns on the way in with your client-side key. And then if you want to process or do queries on that data, what you do is you go and get an attestation that it is SQL Server and it is running inside either a VSM or SGX enclave. You get a cryptographic proof that that's the case. Once you're confident that it is SQL Server and it's running inside of an enclave that you trust, you release your client-side key to it from the hardware security module. So it now goes and can fetch it from a HSM. And at that point, it can start to produce these queries. And you send from your client encrypted queries to the database, so they're queries encrypted on the wire, and you get back encrypted results so that only you can see the results. In fact, these are used with session keys, so they can't even be replayed from someplace else. So this capability, I'm going to demonstrate for you right now. So this is SQL Always Encrypted VNext. And this is running on an SGX server. This is an Intel processor with the enclave in it. While that's logging in, take a drink of water here. So how many people recognize this tool right here? So raise your hands. So a few SQL database administrators up here. This is SQL Server Management Studio. And what I've got here is a query here. Select the top 100 of employees. And what I want to get back is Social Security names, first name, last name, and salaries. And if I run this here, you can see that I get back results. But you can see, or the SQL Studio here, which is sitting on the SQL Server, reports what the results of that query were, but reports garbage for two columns here, the Social Security number column and the salary column. And we've designated those as PII, or very sensitive information, so we want to have those protected with Always Encrypted VNext. Only a client that's authorized to see that kind of data can see it. In fact, but anybody can perform queries that run over that data. So for example, I could perform a query that says, what range of salaries do I have? And so here's an authorized client. It's the Contoso HR client. And what I've got over here is the SQL Server Profiler, which is going to show us all the queries made from this client-side application to the database. Now, this client-side application has authority to go and access and do queries on top of those confidential rows. So it can do queries like, let's take a look at information about the employees in this company. And let's go see employees that have a Social Security number that ends in 70. So this particular client is authorized to do queries on those confidential rows by proving that it's got access to the key. And now you can see that it's been able to retrieve a list through a query that's a sub-expression match on any employee that has a Social Security number that has 70 anywhere in it. It's also able to do range queries over that. So Let's say we want to see salary ranges of different employees. What employees have salary ranges in a certain range? And again, those queries are processed inside the enclave, and the results are sent back encrypted, and this client has authority to perform those encrypted queries because it's proven that it has access to the key that's been used to encrypt those columns. Those keys that were used to encrypt those columns were specified through the creation of the database right here. And I'm having a little bit of a network lag here. So let me zoom in here, and you can see that when we created the database, we specified that the salary column should be encrypted with this key right here, this column encryption key. And same thing with the social security number column. So this client that I just operated with has access to those keys. And you can see that it was able to perform those queries on those columns. But if I go back and take a look at the profiler and maximize here, you can see that the profiler never sees the query. It never sees the query itself, so you can see the search pattern on that salary range is encrypted with a key that only the enclave can look at. So somebody sitting on the infrastructure, somebody that's compromised this, can't even see what kinds of salary queries or social security queries that I'm performing. They can't see the results of them either, and they obviously can't get access to those columns itself. So that's SQL always encrypted vNext. So I'm not sure I understood the question, but let me try to explain what's going on, which I think may answer it. The query is done in the clear, in the enclave. The key was provided by the client, so now SQL Server can decrypt those columns, see the actual salaries, see the actual security numbers, and then process the query. That query came in as encrypted so that only the enclave knows how to decrypt that query and see that it has run a query of salaries between this range and this number and this number. And then it encrypts the result and sends that back to the client, so only the client can see the result. So that's SQL always encrypted vNext. We've been looking at other scenarios too, big data analytics. So Hadoop, most of you probably have heard of Hadoop, a very popular MapReduce type big analytics data platform. We've gone and created a prototype of Hadoop that is using enclaves where the map and reduce functions are placed into the enclaves. So if you trust the map and reduce functions not to leak the data, they can, and release keys to it, to access the data, they can perform these big data analytics queries on top of it. Again, just like SQL Server, the inputs are all encrypted, the output's encrypted. It's encrypted while it's being processed effectively because of the black box, the enclave is protecting it. And here's one that I'm particularly excited about because we hear this a lot. A lot of our commercial customers, and I think even government customers, have data sets where those data sets are interesting by themselves, but would be more interesting if they could be combined with somebody else's data set. But we want to get insights out of the data, but we don't want to reveal our data to anybody else. Multiple parties coming together, combining their data sets, and getting deeper, better insights out of that combined data set. Up to now has been a leap of faith. I trust somebody to see all of the combined data sets to be able to perform those queries on top of it. It might be one of those parties, or it might be a third party, but I'm trusting somebody to have access to all of these very sensitive data sets. This example I've got drawn up here is one we hear about repeatedly. Financial institutions and health institutions like hospitals and health research organizations would love to be able to combine their data sets together to get deeper insights into drug efficacy and treatment efficacy. However, regulatory concerns, data privacy, customer privacy, HIPAA concerns make them reluctant to go and share their data sets with somebody else, even one of these other parties, the research organization. With multi-party machine learning based on top of enclaves, it's possible now for them to get together, take a look at a machine learning function, get confident that that machine learning function is not going to leak any data, that it's going to perform the computation they want, and then have that then stored inside of an enclave, for example, in a cloud provider like Azure. Then what they can do is then go get an attestation that it is that machine learning code running in an SGX or VSM enclave. And once they get that confirmation, they release the key to the enclave. It's encrypted on its way in, so nobody can see it on this way in. The cloud provider can't see it. Every party now does that and makes then available to the machine learning platform their data sets, which are encrypted. And now that machine learning algorithm sitting inside the enclave with access to those keys goes and decrypts on its way, while it's being processed, the different data sets. So they're all in the clear together in the enclave, never exposed, and no party ever sees anybody else's data. And yet they can all make use of the combined output to get better insights. So that one's really exciting to us. I think that this one opens up a lot of opportunities for data sharing that just, even in a world of perfect cloud security, people would just be uncomfortable with. And then finally, this is another one that we're very excited about. How many people have heard of blockchain? Now, this is a trick question, because I think everybody's probably heard of blockchain right now. Blockchain, how many people have heard of containers and Docker? So, yeah, Docker's in the room. Docker in the house, back there. So there's people from Docker, so shout out to Docker. Microsoft's got a great, and Azure's got a great relationship with Docker. Docker, if you go back 3 or so years, everybody was talking about Docker, and for good reasons. Docker and containerization really have changed the way that people develop applications. Today, the big hype, part of the top of the hype cycle is blockchain. Everybody's talking about blockchain. Now, blockchain, for those of you that haven't been following what blockchain is, and maybe you've heard, oh, Bitcoin, that's a type of blockchain. Bitcoin is a type of cryptocurrency. It's built on a blockchain. In fact, it was what blockchain was created for. Blockchain solves a very hard problem, which is lots of people that don't trust each other at all being able to do business with one another. And so it's got some interesting characteristics. It's distributed, so it's often called distributed ledger technology, or DLT. Every party has a copy and can see the ledger. Anybody can submit transactions to the ledger. They use cryptographic keys to basically authorize the transaction. So cryptography is heavily used in this. And then transactions, when they're added to the blockchain, are added in groups called blocks. Now, how does everybody agree that a block should be added to the blockchain, this next set of transactions? It's a distributed consensus algorithm, a very innovative one, called proof of work. So the idea is nobody trusts each other, and we don't want each other doing frivolous things and processing transactions and blocks that are malicious. An example of a malicious transaction would be one that would be trying to spend money twice, or cryptocurrency twice, which would allow somebody to make away with potentially expensive physical goods that they shouldn't have. So this consensus algorithm, proof of work, requires somebody to show that they've got a big investment in this. They're going to spend some energy, and these people that are willing, or systems that are willing to spend that energy, are called miners. The miners are tasked with solving a cryptographic puzzle, which is basically finding some hash of a block that they want to add to the blockchain that matches a certain pattern. And this is an NP hard problem, so they basically just have to go brute forcing through it. And somebody eventually comes up with the answer and then broadcasts it. And then everybody else looks at the answer and says, yeah, it's valid, and then they add it to their blockchain. These blocks cryptographically reference the previous block in the chain. And so that means that with this links of blocks all the way back to the beginning of the blockchain, it's impossible to go and change anything that happened in the past without destroying the chain. So you know if it's been tampered with. So this gives it a property called immutability. And this is great for things like cryptocurrency, but if you think about it, it's great for other kinds of scenarios where people do transactions with one another. Wouldn't it be great if we could have suppliers that all have a common view of what's going on in the system? Or we could have financial transactions between banks where we don't have to have a middleman sitting there and keeping track of where the money is at any point in time, and it's kind of in the middle at some point in time, where we can have the banks directly transact with one another, knowing that it's cryptographically secure and visible to everybody and immutable. So blockchain has the potential to basically transform lots of different industries, getting rid of middlemen, getting rid of waste and fraud, because with the blockchain, it's very hard to have fraud, this double spending thing. And I'll give you a couple examples of places where we see in Azure blockchain being used. One of them is in hotel supply chain. So there's a hotel company called Webjet. It's got a whole bunch of hotel chains. And basically Webjet is a federated company. These hotel chains have inventory, and they've got customers that come in through Webjet and then get assigned inventory from those hotels. The problem here is when it comes to hotel supply chain that there can be fraud in the supply chain. In fact, Webjet, the hotel industry estimates about $10 billion of fraud in hotel inventory every year. So Webjet is looking at blockchain within itself, within its own subsidiary organizations, to eliminate the fraud within itself by having all the hotel inventories be visible on the blockchain, where inventory from one entity given to another entity can only happen once, and everybody sees it and can track it. Another example is marine insurance. So we just did a joint project with Bank of America, Maersk, and Ernst & Young, where marine insurance is being tracked on a blockchain. And if you take a look at marine insurance, it's objects, shipping goods that are moving across ports to different ships and transferring between different entities, and insurance has to follow along, and liability with all of those transfers. And up to now, that's been very difficult to track, and it of course leads to fraud and waste as well, and lots of systems that are designed to try to get a consistent view of what's going on. And so they're applying blockchain for that scenario. Now the problems, though, with blockchain and these blockchain systems are that everything that you do on the blockchain is visible to everybody else. And that's required for people to go validate what these transactions look like, what they're doing, to validate that whoever's minted a block has actually minted it properly. It also has this fundamental problem of proof of work, where to actually mint a block, you've got to go solve some stupid cryptographic puzzle. And it's estimated now that the amount of energy spent on Bitcoin can power a small US city every day. And that's how much money, how much energy is just being wasted by people trying to mine and win the next block. And the incentive to mine is that you get some Bitcoin in return for mining. And Bitcoin's valuation has gone through the roof lately. So the proof of work, though, means that you've increased latency of these transactions. In fact, in Bitcoin, it's 10 minutes. The target is 10 minutes. So the blockchain is self-tuning through a distributed algorithm where periodically the blockchain will look and see how many transactions did I perform in the last n transactions, and how long did it take? How long did it take me to perform the last n transactions? And my target is that a block is mined every so often. In the case of Bitcoin, it's every 10 minutes. In the case of Ethereum, which is another very popular blockchain network used in consortiums, so it's not specifically for cryptocurrency, although Ether, which is the gas for Ethereum network, has also gone through the roof lately in price. That has a target of 10 seconds for committing a block. So right there, you've limited your transaction latency. And then the number of transactions that can go in the block is very limited. And the number of transactions that are processed per second in Ethereum is somewhere between 15 and 25 on the public Ethereum network. Ethereum, though, is one of these blockchain networks that people can go deploy in their own environments, in that case like Maersk, to have a blockchain among different parties. So it's used in what we call consortium blockchain networks. Azure has long been focused on making it easy for customers to use blockchain. And the reason is that a lot of digital transformation now is bringing along with it blockchain. So we want to be a great platform for blockchain. So Azure for Blockchain is blockchain templates in our marketplace for about 10 different ledger types: Ethereum, Hyperledger, Corda, Quorum, where you can go to the marketplace and with a few clicks deploy a single node for a proof of concept, a multi-node for a real network, even a multi-node network that spans Azure regions for disaster recovery and DR. And one of our announcements, as Karina mentioned today, was that we've brought those blockchain templates into Azure for Government. So now you can do it in certified environments. But we've been looking at this from a lens of enterprises and this limitations that blockchain has of lack of confidentiality, lack of throughput, lack of latency, poor latency. Many enterprise scenarios, many consortium scenarios just cannot be built on top of a system like that. And by the way, when I say lack of confidentiality, there have been some steps made to provide some confidentiality specifically for transactions that involve moving some amount from this account to another account. There's been very sophisticated cryptographic solutions for this called ZK-SNARKs, zero knowledge, succinct, and I always forget the rest of it. Yeah, I can't remember. Somebody, ZK-SNARK, and they came up, it's one of those reverse acronyms, like let's come up with the acronym first and then map words into it so nobody can remember them. But those are very limited and very complex and do require you to trust somebody to actually bootstrap the cryptographic material that allows you to do ZK-SNARKs. So I just wanted to acknowledge that. In the general case, though, being able to do very sophisticated smart contracts of not just move this amount from this account to this account, but actually perform logic. And Ethereum has built into it its own language and its own Turing-complete virtual machine that allows you to perform and execute basically programs called distributed applications. Now, these limitations, though, make it impossible to apply in lots of scenarios. So what we realized is that by leveraging these enclaves, so going back now, it's been a little bit of a digression here, but going back to trusted execution environments, you imagine this. We're all forming a consortium network. We all take a look at a piece of blockchain network code that is going to be performing these transactions and these smart contracts, and we all agree that it's trustworthy. Now we all create our own enclaves and store that code in those enclaves. You stored this code in your enclave, and what I can do, my node can talk to your node and get an attestation that it's the same code running in your enclave as is running in mine. And if I trust the enclave to protect the code, then I trust the enclave to protect the data that code executes. And so what I do is I release my key to the blockchain to your node. And all of the parties have this key exchange between their enclaves. So no party ever sees anybody else's key, just that code that's running in their enclave sees it. The combination of those keys allows those nodes to unlock the blockchain. And you can define, using this technique, arbitrary rules around how many people, how many of those nodes, how many of those members have to provide their keys for the blockchain to be unlocked. Because what you don't want is a system where you have 5 participants and all 5 have to provide their keys, because what happens if one of them says, nope, the blockchain's being bootstrapped because there was some failure, and one of the parties says, I'm not giving you my key, the blockchain's dead. So typically you'll have some algorithm, some governance protocol that says n divided by 2 plus 1 have to provide their keys. That way a majority can run the blockchain, a minority can be malicious, can leave, and the blockchain can continue to operate. So we realized that you could build this kind of platform that you could run blockchains on top of that overcome those problems I talked about. Let's talk about latency and throughput. Everybody trusts everybody's nodes because everybody trusts the enclave and everybody trusts the code. That means everybody trusts the output of everybody else's node. So we don't have to do proof of work. We don't have to do verification even to trust the answers coming out. So if I submit a transaction to your node and you process it and give some output that's cryptographically signed by you, then my node is implicitly going to trust it. My node doesn't have to recompute it. So now we get latency that is basically just transaction latency, how fast you can process a transaction on your node. The throughput is, again, how many transactions can go through the node, just like a centralized database. And let's talk about confidentiality. Your node, running the code that we all trust, can have access control policies built into it. Like, let me give you one of the examples. I talked about supply chain. And one of the problems with supply chain is typically you have somebody that is managing the supply chain, somebody a retailer, for example, somebody that is purchasing stuff from different parties. And that entity wants to be able to see all the transactions because they're the ones running the show, basically. But they don't want the individual suppliers to see the transactions of other suppliers with themselves. With commercial blockchain, very difficult to implement that kind of confidentiality policy. But with the model that I've just described, it's possible for the access control list to say, if somebody comes and asks for a transaction, let me check to see if they're a participant or if they're the retailer. And if they are, I'll reveal them those transactions. If not, I'll say access denied. And that access control check is done inside the enclave by the enclave code that we all trust. So now you've got confidentiality built in. So what we've done is, and I'll give you basically a simplified description of this system, but we've come up with a system that can bootstrap itself, can admit members, remove members, use arbitrary confidentiality rules, and we've ported Ethereum on top of it. We call this framework the COCO framework, and we announced this in August. This framework, we've got a proof of concept working on for it, and it's going to be fully open source. We're going to release it sometime in the spring. It has no tie to Azure, so you can take this and run it wherever. And we've gotten several third parties to commit to porting their blockchains, integrating them with COCO framework to get these capabilities. One of them is JP Chase with Quorum, and Intel with Sawtooth Lake, their distributed ledger. They're integrating it with it. And so now with Ethereum on top of it, you get compatibility with all Ethereum code, but you get it with these capabilities. And like I said, it's open source and you can run it anywhere. So it'll be in GitHub, you can take it, you can run it on your own networks on premises, you can have nodes in Azure. We expect lots of customers to run all their nodes in Azure. But because Azure has these other benefits that I talked about, but it directly does not have any connection with Azure. I want to show you a demonstration, and I've got a video recording here of COCO in action. What I'm going to show you here, if you take a look at this left side, this left side over here is a dial. It's transactions per second. It is representing it's talking to a COCO-enabled Ethereum network, multi-node Ethereum network. And then the right side is an off-the-shelf, just taking the pure off-the-shelf Ethereum code and running it on the same types of servers with the same number of nodes, and also displaying transactions per second. What we're doing is taking 2,000 of transactions from the public Ethereum network and handing them to both of these networks we've got, these enterprise networks we've got, and then watching how they perform. Now, I'm going to pick this up right here because we've pressed the compare button, and you can see that over here on the COCO side, that it's actually already finished. So you can see it's processed 2,000 transactions. The average latency was 125 milliseconds. And the throughput was 1,600 transactions per second. Now this other side, we're still waiting for it. In fact, you can see that I'm going to have to slide this forward. And there we start to see it process some. And this is the latency of the mining and waiting for enough blocks to commit before you can consider it stable. So that's another limitation. If you're interested in the details of blockchain, you can't just wait till somebody broadcasts this block is the next block, because somebody else can come along with more proof of work and say, no, that block isn't the next one, it's these 2 blocks. So before you actually take action on any result, you basically have to wait a while to have enough blocks or enough depth or weight on top of the block you're interested in to actually take action on it. So we have the Ethereum network waiting for 5 block commits before it takes action. And that adds to the latency, because on average, each block commits in 10 seconds. So we're talking about over a minute before, typically, we're waiting for the first batch of transactions to commit. You can see that here it's only processed at this point in time 778 transactions, and now we stop the video, and you can see that it's at 2 minutes in. And the transaction throughput was basically what you get with the public Ethereum network, about 13. So I said somewhere between 15 and 25. So that's Cocoa in action, built on top of SGX enclaves and this confidential computing.
How do you solve the problem of concurrency? Right, in the Cocoa, you're just accepting, you're not revalidating everything.
Yeah.
So, how do you solve the concurrency issue?
So great question. How do we solve concurrency in Cocoa? We don't actually have to use a distributed consensus algorithm. We can use a more centralized consensus algorithm like Paxos, and that's what we did here. We're using Raft, which is an open source Paxos consensus algorithm, popular with open source projects. So we ported that into the Cocoa framework. But you can bring, and we're actually doing research in other consensus algorithms that scale better than Raft to have larger networks. So this is an active area of ongoing research. Now, when I talk about Azure Confidential Computing, let me talk to you a little bit about what this is. Like I said, we've been working on it for 4 years in Microsoft Research. And we've done proof of concepts on all these kinds of scenarios that I've shown you, including taking some of them to production like SQL Always Encrypted and Cocoa. The set of capabilities that we're releasing include SGX-enabled hardware. Like I said, we're the first cloud to have SGX-enabled hardware. If you're interested in getting access to the preview, let us know. We've actually already filled it with the interest that we've gotten, but we might consider you, if you've got a really special use case, fitting you in. And we also we're developing SDKs, runtimes for the enclave that provide services for the code running in the enclave, compilers that enable you to ensure that the code has no side channel leaks, because that's another weakness, for example, of code that you put in somebody else's environment, is they can go sniff what it's doing on the cache or memory to try to figure out what algorithm or what keys it's got. So we've developed compiler technology in Microsoft Research, which is called oblivious computation, which you can look at it and you can give that algorithm two very different data sets, and the trace through the cache or through the branch table will look exactly the same from run to run. So you won't have any knowledge leaking, any information leaking about the data. And so this whole package of features that allow people to create confidential computing algorithms and code is what we're going to be bringing out over the next year or so. This is a first step in, I think, like I said at the beginning, in a new world of cybersecurity. I think that when I look ahead at what the promise of this is not just for this small scale, just stick a little piece of code, process some data in it, but building basically networks on top of it that are enclave networks, where all of the data within the network, and you see Cocoa is kind of a form of that, all of the network data in that network is encrypted and accessible only by the code in that network, not by anything else. And so we can imagine complex applications fundamentally being built on top of this technology and keeping data fully secure while it's in use at all times. We're working with Intel and other hardware partners to advance the capabilities of this type of technology, and also advancing our own software-based technologies. And so I think that if I look forward 5 years or so, maybe 5 to 10 year time frame, this will be table stakes for anybody building applications that have any data sensitivity, any data security. These types of technologies will be part of every application in that kind of environment, would become table stakes. So I think it's an exciting world. It's really fun to be part of getting it out and pushing the envelope on this. But this is just one example I wanted to highlight for how we don't just take and say, oh yeah, we're going to check the boxes on cybersecurity, but we're trying to think about how we can push state-of-the-art forward. And this is one domain. We're doing this across lots of different domains. Artificial intelligence, of course. You've heard quantum computing. We're trying to push the envelope on that. But that's our mission in Azure, is to create a platform that people can do really cool stuff on, and securely and at scale. So with that, I've probably run way over time, haven't I? Okay. So I don't know if we've got time for Q&A or if you just want to jump right to the... Got it? Okay. All right. So thank you very much. I hope you found this interesting.